welcome back. So now in this session we are going to view about global optimization with Matlab. So basically we have view in morning session that Matlab has different modules. Okay. MathWorks is having different modules. So in that one we in math and optimization section we have this optimization and global optimization. Two tools are there. So we start with this one. So whatever our agenda is right now, so we just look about that what is the global optimization, introduction about the global optimization, then survey of solvers with different examples like multi-start, global search, pattern search, simulated annealing, genetic algorithm or multi-objective, both of the things. Okay. So right now you are viewing this image in this slide. So here it's a self-generated image by peak syntax. So it's an inbuilt syntax peaks which will allow this particular image to open. So we have global minimum. So because of we are going to find out optimum solution for our problems. So local minima is any solution in your problem which will we can find out from any solver, and global minima is the best solution which is suited for your problem, which can be find out by different GA tools. Okay. So we start with this. So just we have a process we have designed that our model or prototype is this much. So we passing some inputs from this. If our object is achieved, so that is our optimal design. If it is not achieved, we modify our design parameters. So basically the optimization process is this much to getting the optimum or best results or best parameters for my design. So what we do, we have an example. So here you will view this particular black point is there. So we have taken this as a start point of ours. Okay, and manually we have with trial and error methods we have simulate this one. So we find out some different points on this one as a solution point of us. But in actual this particular region, actually this is a energy diagram with pressure and rotation of motors. So this particular region is our main that means whatever the solution we are getting in this particular region, our solution must be there. So by manually or trial error methods we are performing, so we are getting this particular solutions. When we choose any solvers or we can say optimization processes, so we get this particular solution in this region itself, you see. Okay. So by using optimization processes we can find out the best solutions or best parameters for our prototype or design. So for this what we get, we find better or optimal designs, okay, as well as faster design solution. So because of we get easily and in a faster way the best solutions for our designs, we can implement that parameters directly and we can create a faster design for us. And it's useful for trade-off analysis with n dimensions. Whatever the dimensions you have, you can run out this one. As well as sometimes some non-intuitive designs may be found, like this particular antenna is there. So this has been designed by GA tools, or you can say right now global optimization. From this release GA has been changed to global optimization. Okay. Now we come up with some example. So we can open Optim tool. So if we are working on optimization or global optimization, just we have to open this GUI tool if we want to work on GUI itself. So Optim tool. So this GUI will comes in this one. This particular is problem specification area. These are the options area. As per your solver, these options are automatically changed, and this is your quick reference. Like we are selected this f min con right now. So you see that all f min con, whatever the parameters that solver and algorithm, so it has showed that whatever the solver and algorithm is there. Then what is your problem? So you can define that at object function. So everything you can define directly in this location itself. Okay. Fine. Now what we do, we just take a simple example in this one. Okay. So we say at x asterisk sine of x plus cosine of 2 x. Okay. So, we have taken this particular problem right now. Now, what we do, because of we do not know what is the start point. So, we can define just a start point to some value and some lower bound, because of we do not have any inequality or equality in this particular problem. So, we define just lower bound to 0 and upper bound to 10. Okay. So, right now we are solving this with f min con. Okay. Say start. So, what it do? It runs simulation, but it says that trust region reflective algorithm does not solve this type of problem. So, what we have to do? We have to change up our solver to active set. Okay. So, we change our algo to active setup, because of we do not know right now that what particular solver is suitable for this particular problem. So, we are just solving with rough estimates or manually, and we are running this one. So, what we do right now, we just define some output functions in this one, custom output function. Oh, okay, and again I run back with active set. So, now my optimization is running. So, this one is the start point which I have given as 3, and rest of the is finding as a solution. So, right now it is getting that this particular is my solution point, this particular. So, whatever the result is coming by this is 4.825, but still we do not know that this is the appropriate solver to solve this type of problem or not. Okay. So, for that what we do, we just first see that what type of solvers are available in optimization tool. Okay. So, as per your problem, if your problem constraint is constraint type none, so linear, quadratic, so whatever the available functions are available, so every function is shown in this particular chart to you, as well as you can find out that different type scalar minimization. So, formulation is this much, okay, and f min bind solver we can use unconstrained minimization. So, we can use this particular solver. So, every solver is given. So, right now what we do, we just go back in our problem and we solve our problem with this solution itself, because of x has taken as a scalar and lower bound and upper bound we have defined in that one only. So, we just find out that f min bound. Okay. So, we just selected single variable, yes. Now, you see only our problem is there, as well as lower bounds and upper bound, x1 and x2 is there. So, no start point is there for me. So, what we do, we just define initial guesses, same way I can define the output function to plot these things. This is just nothing, some plotting techniques has been written in that particular program. See, so some plotting techniques has been written for lower bound and upper bound, each and everything they have written for this. Okay. So, we clear this result and again run back. So, right now we have not defined any start point, it will automatically taken care of start point and start the problem for solution. So, right now we are getting this particular red point is my best solution. So, it is again giving 4.826, but still we are not getting that this is my start point. So, what I do, I just define some more start point in this one by f min con solver, and again we are going to find out that this is the appropriate solver solution for me or not. So, what I do, I just start one script. Okay. Same problem we have written by command line itself. So, we have defined the same problem in if variable, lower bounds and upper bounds we have defined, and we have just find out on these particular initial points, startup points. We have 0, 1, 3, 6, 8 and 10. Okay. So we run this one and we executing this. So we are getting this particular for each and every start point. First we have taken 0, then 1. So for each and every we are getting the different solutions in this one. Okay. You see. For this is my function value results for every point. So whatever the points we have taken, as well as so now what we have seen that whatever the methods we have tried, but we are not getting the optimum solution, whatever the optimum solution for our problem. So for overcome with this one, what we do, we have seen this with f min con, but it will not find the minimum for the function, minimum value for the function. So we have executed this. Same as one, we have one more problem for nonlinear regression. We can discuss this problem also. So you see this particular, it's showing these particular points is generated by points, and by fitting we are not getting exact fit. So to overcome with this one, as well as in this particular problem, which we have seen earlier also. So for all these problems, we are going to solve these things by different solvers. So what we do, we must first see the same problem which we have seen. Okay. By global search. So what it do, it will automatically implement each and every solver, whatever the available solvers are there. So it will implement each and every solver on my problem and find out the best results for me. So I just execute this. Okay. So right now I'm getting the exact solution, and it will all 30 local solvers run. So every solver is going to run in this one for positive local value, and we get this XGS as my result value 4.79454. So what we have seen, that we have used f min con first, we have used f min bound first, because of we don't have any start point, so we have defined that, but we are not getting exact solution. So what we do, we just define in global search. So what it will do, it will automatically implement each and every solver, whatever the available solver in optimization and global optimization, it will implement every solver on that and find out the best solution for you. Okay. Now with global optimization, because of I already told that in that problems we can find out any solution, that is our local minimum, but we have to find out our global minimum, which is shown in this particular restrings problem. So in this one, number of local minimums are available, but we have to find actual global minima, so which is available on 0, 0 point, where x and y axis are 0, 0, that point is available over there. So we have to find out that particular. So in this global optimization, our goal is that to find out the lowest or largest value of nonlinear function that has local minima or maxima. So we are going to, so what is our problem? So traditional solvers often return one of the local minima that we have seen earlier, but if we are using global optimization along with optimization, so that we can easily find out those values in this. Okay. So simple solution to use a global optimization with multi-start, global search, generic algorithm, pattern search, simulated annealing. So we are going to use one by one each and every solver in different problems. Okay. So for these two tools are available, optimization and global optimization. So optimization can be implemented in these particular problems where faster and fewer functions equations are there. So you can use up those tools. For larger problems and higher dimensions, you can use optimization tool. To find out global maxima and minima, we can use global optimization tool. For better or non-smooth, non-smooth stochastic discontinuous and undefined gradients, wherever these type of problems are available. So, you can use global optimization tool in this, as well as for custom data types we use global optimization. So, this is just a chart where to use optimization and where to use global optimization in this one. So, we have seen that earlier, that peaks figure. So, we are going what peaks will do, see, whenever I call that peak syntax, it will display this equation as well as this peaks curve for me. So, we are going to find out that what is the local minima and maxima in this particular figure. So, we just start up with okay. So, here we are just calling that peaks function, and whatever the my constraint function is there, this particular function, where equalities has been defined, nonlinear equalities has been defined. So, we are going to execute this particular file. So, in this section what we have done, we are finding our objective function, that is peaks. That particular z function is callable in command window, same as the constraint function defined. Then we have defined a problem. So, what we have done, we have defined a problem in structure format by using create optim problem. So, this is a syntax by optimization tool. You can view this. So, here just we have to define each and every property what we are going to define in our problem, that what type of solver, lower bounds, upper bounds, equalities, inequalities, any other function, constraint functions. So, each and every function we have to define in this one. It will create a structure type of format for you. So, okay, so what we do, we just go back and reset ourselves and execute one by one. So, first it will generate that curve for me, then it will show, this syntax will show that what type of constraint function we are using. So, this constraint function we are using right now. So, type is the function which will display complete file, whatever the contents has been in that file. Now, we are defining our problem. So, we just define our problem with solver with fmin_con, objective function is at x peaks, whatever we have defined earlier, and nonlinear constraints are this particular file. X0 is defined as initial case is -1 and -1, lower bound is -3 and -3, upper bound is set to 3 and 3, and option is set to optim set output function to this particular plotting file, where we have defined few of the syntaxes for plotting. So, what we do, we just execute this. See, so my all problem has been defined in this particular problem variable. So, this is a structure objective function. So, whatever the handler we have, okay, x0 values, inequalities, we do not have any inequalities, as well as equalities, only lower bound and upper bound. So, we have defined that. Nonlinear constraint, define solver fmin_con, and option is set to some particular file. Now, what we do, we just first run for only fmin_con this. Okay. See, taken from a start point, from this particular point it has taken and end up in this local minima, where we are getting that particular point, local minima point. But this is not our optimum solution. So, we have seen that right now we are using fmin_con, but we are not getting the minimum solution for us. So, now what we do, we just use the multi-start. Okay. So, what multi-start will do, it will find out multiple number of start points and find out the global solution for us. So, for that what we do, we just define multi-start in a variable. Okay. Now, we just run multi-start with this syntaxes. So, we have to store x, f, function value, exit flag, outputs, everything we are going to store in this one, and run ms with problem. So, you see, it started first, second, third. So, right now it started and find out the last solution on this particular point, which is our global minima. So, by multi-start, what it will do, it will start with number of points, find out the number of minimum value, and it will start with those values and then get back optimum result for your problem. So, what we get, Okay, so these are the outputs of 0.2282. Same we have seen in this multi-start, that what multi-start is, it's run a local solver from each set of start point. So we have seen that it started from each and every point, like here it has find out multiple number of points and start from each and every point. Suppose that one of the point is this particular point, this particular point, this particular point, and this particular point. So it will searching from these particular points and get back result, whatever the optimum result for our problem, it get back to us that thing. And it's option to filter starting points based feasibility. So whatever the different starting point feasibility, we don't want to define any starting point. It can automatically search out from those regions for you. As well as these syntaxes are supported by parallel computing, because of sometime what happens, your problem is too big. So that will take a long time for simulation. So what we do, we can bifurcate that problem with number of CPUs. So that we can easily run in different sections. So what we do, we just see one more example. This curve fitting, whatever the curve fitting problem we have seen right now. So we start up. So right now we have generated some data in this one, okay, and we are going to just plot that one. So we are getting this one. Now we have, if we are performing some fitting with normal solvers without using multi-start or global search or any GA solver. So see what happens to the result. So here we have defined our objective problem in this one, 3 compartment model. Okay. Now we are same problem by using LS curve fit, linear square curve fit problem. We are using our model, okay, X data T and Y data C, and rest of the initial conditions we have start points we have defined, lower bounds, upper bounds, and some output functions. Now what happened? Okay, now we just solve our problem. See, our data points are this much, which we have taken earlier, and the fit has been performed in this location. That is not good fit for us. By using fmin conv, right now we have performed this one. LS curve fit. Okay, so we have defined this. So for each and every point, we whatever the points we have given 1, 1, and 0.25, we are getting this. This is fitted value, which is not actual value. Now what we do, we start with this one multi-start. Same way we have defined the ms variable with multi-start and run that again. See, it's find on each and every point whatever the best fitted result, and it can fit on actual points, whatever the actual points are there. Okay, so this has been find out on this particular points, it has been fit. So starting value has taken this one, and the find optimum value is this one for B1. For every point it has find out. So this is the by using multi-start we have done. Okay. So this is my solution, final solution. Now what we do, we just empty that output function and finding out that what is time taken by normal computation by using single CPU. So what we do, we just execute this. So it's executing. So it has taken around 10 seconds to simulate this problem. Now what I do, I just use both of my cores. These both cores I am going to use, okay, for solving this particular problem. Okay, so just we have written Matlab pool open. If you have parallel computing toolbox, so we just write this syntax Matlab pool open. So it will allow both of my CPUs to work, and set the parallel in that particular problem, that always you have to use this particular parallel option. Then again we run back and close that loop. Now we execute this. Basically what it will do, it will run 2 instances of Matlab on, right now might be it will take time because of I have to give an access to that one. So it has taken around 6.8 seconds. So almost we can say around 32% time has been decreased by. So if we have multiple number of processes, so we can decrease more time in this one. Like say we have 16 cores, or on a single PC we have 8 cores, so we can decrease more number of times. So parallel options can also be usable in this global optimization or optimization tools. So we have seen this multi-start with parallel also, without parallel also, how to solve these things. Now next thing is that global search. So we are going to globally search by using local solver and find out the result, that what is that result. Okay, so what is global search? It's a multi-start heuristic algorithm, similar to multi-start it is, but what it do, it will remove that number of points which is not necessary, local minima, remove that particular points. It take up only that particular points which are nearest to global. So calls fminCon for multiple start points to try and find global minimum, whatever the global minimum of my problem. Then same filter and removes non-promising start points, whatever the start points are non-promising, it will remove that particular points from this. So we start. Same problem we have taken, that peaks problem we have taken, same nonlinear constraint, just what we have done, we have changed to global search. First we have solved out by similar that particular problem, and then change out the solver to global search. Okay, so we run back. Okay, same solution we are getting. fminCon, so we define global search. Now we are running with global search. Okay, so this is my endpoint. So this is my global point. Last point is this much. So you see that in multi-start it has run number of times. I can say 5 or 6 times it has run, but right now it's run 4 times only. Solve out the solution to get back the solution. So by using global search, we can find out different results. So we are getting okay. So we are getting that much iterations taken care by that problem, 17 iterations. Function count is 60. Okay, step size, whatever the algo they have used. So each and everything has been defined in this location for you. Function same as function value, x value, everything. Like we want to find out the x value. What is the x value? So this is your x value for each and every solution. Okay. Now the next step is simulated annealing. By using simulated annealing, we are going to solve out different problems. So what is simulated annealing? It's basically using by annealing of metallurgy. So that what we do, we just find out the cooling temperature point. Okay, so wherever the nearest cooling temperature point, it will find out the global minima at that location. So by analogy, we can say simulated annealing replaces a current solution by randomly choosing a nearby solution. So whatever the nearby solution is there, so it can taken care by this one. Okay, with temperature it's defined. So already told that thing to you. So what we do, what I do, I have one file, this particular file. Okay, in that one, no MATLAB syntaxes has been written right now. Okay, so but what we do whenever we publish, we see that in morning that publishing option. So what we do, we just publish this particular file in HTML. Now it has created a link for me for each and every whatever the demo files we have. Each and every link has been created, as well as sections. So different sections are there. So what we do, we just set up things for that demonstration. Okay, so what we do, we just see this peaks minimization by simulated annealing. So for this, whenever we click on this one, it will automatically simulate that thing for me. So you see that current x values has been changing from one point to another point in this. Okay, so whenever it simulate, it will show the results to you. Basically, we are executing this particular. Sorry. So here it's executing for number of syntaxes. Number of times it is executing that whatever the iterations is taken care by. So what f values, x values has been come out. So it has 300 iterations taken care by this one, and whatever the value for each and every step, that has been shown to you. So what we have executed, basically, we have executed this particular file, the same file, by using that particular HTML help. Same circular constraint we have defined. We have defined a problem fmin with fmin con, and just we have changed back to solver to simulated DND. Okay, and same objective problem is there. Whatever peaks problem we have taken, as well as the constraint problem we have added up in this one, and SA optimization set has been defined in this one, and we find out the solution for this. So what is the x and f value from the problem? We just take it back in this one, and we get back this particular all iteration results. Or we can solve this Queen's problem. So basically what it will do, see, this particular is a chessboard, in that 8 queens are placed. So each and every queen is attacked to everyone. So we have to find out the optimum solution so that no one can attack each other. For that we have write this particular program. So now when we execute this, it will automatically find out the global solution and place. See, automatically it has been changed, number of attacking queens. So from on which place queens are attacked. So all has been done. Now no one is going to attack each and everyone. So we have just solved this problem by simulated annealing foundation problem. Okay, so here this just a function plot board which has been written below. So it's going to create a plot of this particular function plot board. So it is creating that figure only, and that whatever the queens you are viewing, that particular this one, this is come by this JPEG image, PNG image. Okay, then we have performed, these are just plotting techniques, and here we have performed this simulated annealing just by defining. So what we have seen, that just we have defined whatever the visualization effect we have given. Apart from that, similarly we are using for each and every solver. Just we have to define the objective function, if constraints are available, nonlinear constraints are available. So we have to set up those things, whatever the linear bounds, lower bounds, upper bounds, or equality, inequality. So just we have to define that things, and we get our results back. Okay, Now next is pattern search. Earlier it's known as direct search in this one, but right now it's known as pattern search with this. I don't have any figure. We have a point. So what it will do, it will vertically up and down and left and right. It will create a pattern for this one. Then it will find out the nearest point for that particular pattern. Then again it will reduce the size. That means contract to reduce and increase again. So, and find out the nearest solution. If it goes to from the lower bounds and upper beyond lower bound and upper bound, so it will neglect that those particular values, and again find out some best solution for this and get back the results. That means it's creating a mesh kind of thing for it. The same things, it will create a different poles on the mesh and find out the results for you. So just see that problem. Okay, so same problem we have taken. So again started, and this is my endpoint. So see, whenever first we have used simple fmin con on the peaks problem, then we have used multi-start, global search, simulated annealing. Now we are using pattern search. So whatever we are getting the best solution in lesser number of counts. So we are right now run that pattern search. So only on the 2 runs we are getting this particular results. And how many number of iterations it has taken? See, only 5 iterations with 358 counts. Earlier we have run around 1000 and 1060 runs we have run in this one. Same way, it's an inbuilt demo of Mount Washington demo. You just see this. So it will automatically call up these values for you, that function values and all defined values. So we have to find out the highest peak on the mountain, Mount Washington mountain. So we just say start to this. So your optimization is running. Now it's finding out. So we just increase the speed. Just see, it will find out each and every point on that mountain, and wherever it get the highest point, it will, this one is our highest point. So it will find out that this is my highest point with red marker. Just we have defined that pole method, what type of mole method we have using. So every option about that pattern search we have defined in this one, as well as same we have defined some customized function in this, and we get that particular result. Okay. Now the last operator is generical, by using generic algorithm GA and GA multi-objective is there. So for generic algorithm, what exactly do from evolutionary biology we are using this particular one to find the exact approximate solution to optimize our problem. So what we do, we start with initial generation of candidate. That means we have taken some of the parents as to find out the selection of the parents with best suitable genes. Then we find out that whatever the child is generated by those particular parents. Okay, so it taken subsequent generation evolved from first generation itself through selection, crossover, and mutation. How it will perform, like like we have taken that binary case we have taken. So in this one, retain the best performing bit strings we are taking in this one, and to favor the reproduction. So here we have taken that parent number 1, which will include this particular bit strings in the 1 zeros form. Same as parent 2 we have taken. So we just find out the parent 1 and 2 for crossover. We have passed on this. We find out this particular child with best, whatever the best genes are there. So we have taken care of this one, or we can say global minima or global maxima values are there. And in mutation, what they have done, we are choosing the best from both of the parents and just reproducing a child with this. Okay. So we just see same thing on peaks minimization. Okay, so you just find out this particular endpoint automatically. Now here you see it's running only 5 iterations generations, and whatever the iteration is taken care by 5220. Earlier we have seen that in pattern search we are getting lesser number of this one. So it is finding the optimum solution for me, but in more number of iterations. But if we are using pattern search, so we are getting in lesser number of iterations, but generation is taken care by same number, 5 number of generation are using. Okay. So you are asking about the particle swarm example. So this one is for you, particle swarm example. The same problem we have defined by mesh grid. We find out the restricting function in this, and just we define that contour plot for this, define our problem, GA optimization settings, and population size we have set to some value. We just execute this. So we are just finding the optimum solution, whatever the optimum solution for this. So every point will come on that single red point. So this is our optimum solution at that moment by using simple GA solver. We have defined the upper bounds, lower bounds, everything, restricting function by GA problem. By mutation of children, this function is callable. So everything has been defined. So in this one, just we have, okay, so this is our objective function which we have taken care, and by GA we have run with GA multi-objective directly that function over there. So we just execute this. See, the similar GA for multi-objective, it has been defined. So what is my objective function? So this is my objective function with f1 and f2. Two functions are there with sum of some particular value and with sum of some particular value. So we just find out that because of in this one we in optimization tool or GA tool, we have to pass on any of the inputs in single variable. Like if you have multiple number of variables available in your problem, so you have to define in single variable x1, x2, x3 like that. Same as an output function. So we have defined multiple function with f1 and f2 in that particular file. You see this one, same f1 and f2, and my output argument is single as well as input argument is single if we have multiple number of x also. So here we define that xi, number of i's is changing with this one. It's just a comparison of all solvers that what is done. So it's running my each and every problem and find out the comparison chart between that. So basically it will create a chart kind of thing, how much iteration it has been covered, how many generations. So it will show that particular chart for you. I don't know what's coming. So these are the techniques which we implement in GA and optimization typically, just by defining our problems, constraints, linear constraints, non-linear constraints, equalities, inequalities, everything we have to define in that, and just run by different solvers that whatever the best solution for us we can find out with this one. So any question from you? GUI method. Okay, so we are opening optimization tool. So here you can choose up different solvers are available, whatever the solvers of optimization or global optimization, that all solvers has been showing in this location. So you can choose up directly your solver from this location. Like first we are choosing this genetic algorithm. Okay, we choose genetic algorithm with multi-objective we are choosing. okay, and the same function which we have used over there, this particular function. Okay, so we just copy this one and we just define it, our fitness function with how many number of variables are there. So we have to define that how many number of variables are available. So just forget that. See, in this GA multi objective, so we have to define each and everything, that how many number of variables are there. So 3 variables are there, and equalities, each and everything. We don't need to define that things. So we just say 3 number of input variables. Everything we just leave it blank. Okay, and we say start. So it's running. Number of iterations. So showing the results on different location to you.
So initial range we also has.
Yeah, initial range we can define, and options we can define. This particular population size.
This we can vary in this population.
Yes, we can vary. We can view on different result, different population sizes itself. Like population size, we can specify right now on 100. Okay, and clear the result. So we have to export our to workspace, that solutions, export that results, optimization results. Okay, so we can view that x values, all x values are there. Okay, as well as we can view that function value, that what is the function value on that for both functions, because we have multi-objective functions, so all functions are there. So we can view. Okay. So this is my function value, and these are the x values for each and every function point. These particular values has been taken. Rest else, what you can define in that GUI. According to solver, it will automatically change up that particular options, whatever the options are there. So here that population size, like has been shown, what selection you are using in that. So each and everything you can define. Reproduction, for mutation, if you want to set up anything in this one, so you can set that in. For crossover, same also. So as per your problem, you have to set those things in this. And rest on below, these are the output functions are there, like different plot functions are there. If you have your own output function, so you can define your own output function by defining in that into a function file and use as a handler. Why we are using this add operator? You know that thing. This add operator, we are using this because of we want to define that as a structure form or that thing. So we are defining this as in add form. Like what we do, we just say x is equals to this particular function we have. So if we define that, see, x is a function structure handler. So it can be easily callable anywhere. Just we have to define with this name, or we can define in variable and we can call up directly that variable. Rest of the things taken care by tool itself, so it will automatically pass on some inputs in that and get back results in.
These all illustrations that you explained are already there in the Matlab directory somewhere, so that we can have future reference.
No, for future reference, there are lots of examples are present in this problem. Some demos are also there. These are not available over there because of they are provided by Mathworks to us to provide as a demonstration purpose. So yeah, these are all present with different examples. They are present, like global search. A few of the programs are also available in this one. So some demos like pattern search are there, simulated annealing. So everything is available for you. Thanks for your patience.